Okay, in this presentation we are going to look at the gamma distribution. So the annual rainfall in inches in western Colorado is modeled by a distribution with the following cumulative distribution function. So here we have f of x, and it is the component of four terms here. So 1 minus e to the minus 0.2x, okay, minus 0.2x times e to the minus 0.2x. So we have e to the minus 0.2x again, and then minus 0.02x squared times e to the 0.2x. Okay, so essentially, apart from the first term, we have e to the minus 0.2x in each of those expressions. So just make a note of that 0.2x. So what we have also is expressions in terms of x, so x 0.2x here and 0.02x squared here. You could say we have an expression in terms of x to the power of 0 in this first term here, which is 1. Okay, so that would be consistent also. Now, where x is between 0 and infinity, so determine the mean and the variance of the rainfall in this region. Okay. Now, so what we have here is a random variable, Wn, which follows a gamma distribution with shape parameter n and a rate parameter lambda. Okay. Now, the cumulative distribution function, the survival function, and the density function are given as follows. Just as a quick remark, there are multiple specifications for the gamma distribution. Now, just one thing that makes this particular formulation of the gamma distribution particularly interesting is that n here is specifically an integer, okay? And also the rate parameter lambda, which usually corresponds to what we would sort of expect for the Poisson and exponential distribution, okay? So it ties in with those, so that's why we might use lambda. Now, the reason I sort of mentioned that is because in the generic form of the gamma distribution will be denominated in terms of rate parameter alpha and shape parameter beta. What we could do is consider some random variable x, that's a gamma random variable, so here just g for gamma, and the parameters are alpha and beta. Okay. Now the thing about alpha in the generic case is that alpha can be any real number. Okay. So it can be an integer or it can be a fraction or anything like that. Okay. So what we have here in this particular instance, Wn, is that n, the shape parameter, is an integer. Again, just to highlight that point, the rate parameter is denoted lambda, really just to sort of tie in with the usual applications of this that would be sort of consistent with the Poisson distribution and the exponential distribution. But really, there's not a whole lot of difference there between using lambda and using beta, to be quite honest with you. But the n is important there, just to sort of emphasize it is an integer. Now, the reason why that formulation will be important is because these particular specifications of all of these things, the survival function, cumulative distribution function, and the density function, all rely on n being an integer such that it is tractable. In the case where alpha is not, where we're using alpha when it's not an integer, it's very difficult mathematically to sort of come up with closed form solutions for these. So it helps a lot that n is an integer, and we rely on the fact that n is an integer for some of these. What I'm going to do is focus on, just for the sake of brevity, focus on this particular part here. Okay? Probability of Wn being less than or equal to t. So this is the cumulative distribution function of Wn. Okay? And that is 1 minus the summation from k equals 0 to n minus 1 of this expression here, e to the minus lambda t, okay, let's just make a note of that, times lambda t to the power of k over k factorial. So what we want to do is match that up with our expression above. And it's useful to note this e to the minus lambda t there, because we do have an expression that corresponds to an exponential term. E to the minus 0.2x, and you notice that it's consistent throughout. Okay, so this is a function of x, or the cumulative distribution is expressed in terms of x. So essentially what we can sort of remark upon here is that lambda equals 0.2, or must equal 0.2. Now what does that mean for the other parameter, which is n? Okay, so here n, what we have here is a summation from k equals 0 to n minus 1. Okay, and where would we see k in the expression? Here, the highest power. Okay, the power of the each terms here. So essentially what we're looking for, the highest power. Okay, and what we have here is the highest power there is 2. So this is n minus 1. So necessarily n is equal to 3. Okay, we can check a couple of things true here. So what we're going to do is let k equal to 2, which is n minus 1. Okay, so what we have here is e to the minus lambda t, which is e. That's straightforward enough. So we'll sort of concentrate on the other part. E to the minus 0.2. We'll just denominate it down here in terms of t, but it's actually x. So lambda 0.2 times t, square that, and divide it by k factorial. That is 2 factorial, which is 2. Okay, that works out to be e to the minus 0.2 t times 0.04 t squared divided by 2, and that essentially works out to be 0.2 times t times 0.02 t squared. Okay, now what we could do there is actually just remark that it actually was in terms of x above, so we could just interchange x there. And yes, that's actually what we have in this line here. You can check it for x equals 1 and k equals 0 and k equals 1 as well. So it should work out. So I'm happy enough with this answer here. Lambda equals 0.2, n equals 3. Now, so what we're asked to do is calculate the mean and the variance. Now this is actually straightforward enough. Using the setup of n and lambda, the mean is calculated as n divided by lambda, which is 3 divided by 0.2, which is 15. Excellent. And the variance is n divided by lambda squared, which is 3 divided by 0.04, which is 75. So that is the answers we're looking for, 15 and 75, the mean and the variance. Good. Done.